All right, so let's go ahead and get us started. This lecture is being recorded, so I'm sure people can go back and watch if they have to. So if you want to turn on your camera, that would be totally fine. I actually encourage it. Kind of increases the participation a little bit. If you don't feel comfortable, that's totally fine as well. Anytime during the lecture or during this review, feel free to unmute yourself and ask a question. And you can always type your question in the chat, but I won't get to those immediately. I will pause once in a while and then get to the questions if you have any questions. All right. I have plan A, which is using my iPad. We'll see how that goes. If not, I have another plan in place that we can go ahead. All right, so my name is Ali Amiri, and I'm a faculty member in the Mechanical Engineering Department. One of the courses I teach is statics. So today, in 1 hour, 15 minutes that we have, I'll go over basically 10 chapters of statics. That's what we're going to have. Very briefly, I'll mention some brief theory, but it's mainly going to be focused on examples and examples that I'll do. All the problems and examples that you see here are from actual FE exam, and they're from the practice exam pack. Okay. Question 1. We'll start with some easy stuff, and then we'll get a little bit more complicated. So question 1 is the magnitude in newtons of the resultant of 3 coplanar forces A, B, and C is most nearly which? A, B, or C? So before doing this example, I want to give you a little bit of theory here. Let's see. Okay. So in general, when we're talking about components of a vector, X and Y, there are two forms that the vectors are going to be given. Okay. Vector F. So a vector is something that has a magnitude and has a direction. And we have to know both of those to fully define a vector. The magnitude here is F. Direction, we are usually 2 ways of showing direction. It's usually an angle with one of the axes, or what we call a slope triangle. Okay. I'll go over case number 1, angle, theta. So to find components of a vector, you go parallel to one axis, in this case parallel to y, find intersection. That will be your x component, f sub x. And then you go parallel to x, find intersection with y-axis, and that will be your component y. So now, since this is a parallelogram, this length here on this side is also fy. So we are dealing with a triangle, fy or f sub y, f sub x, f, and theta. So in this triangle, if I want to write cosine of theta, I will have f sub x over f. If I want to write sine of theta, I'm going to have f sub y over y, or over f. So therefore, my fx would be f cosine theta, and my fy is going to be f sine theta. So this is how you find 2 components of a vector if an angle is given. This angle can be with any of the axes, x, y, positive x, positive y, negative x, negative y, doesn't matter. As long as you can see that triangle that we have, you're able to figure it out. So that's the angle. The other way that they usually show in problems is something that we call a slope triangle. We're going to have same force, same direction. Instead of giving an angle, sometimes they give a triangle like this, A, B, and C. So this A, B, and C is similar to this big triangle. Okay, so we can assume a triangle that this length is A, this side is A, this side is B, and that side is C. Any two of them would suffice. Okay, so if we want to find fx and fy again, same as before, let's assume an angle. If this was an angle alpha, okay, sine alpha would be B over C, and cosine alpha would be A over C. Okay, so now we're back up here again. These two. So all I have is fx is f cosine that angle, which is going to be A over C, and fy is going to be f cosine that angle, sorry, sine that angle, which is going to be B over C. There is no angle in this one, okay? Because that A over C and B over C replaces the sine and cosine. So these are the two common ways that vectors are given as far as the direction is concerned. And you should be able to find the components of a vector. Okay, questions so far? Okay, so let's go back to the problem that we had. The magnitude n of the resultant force, 3 coplanar forces, A, B, and C is most nearly. So coplanar, that means they're all in the same plane. Okay, so, and that plane is just XY plane. So basically it's a way of saying these are all 2D vectors, okay, which we can get from the figure, but that's the meaning of coplanar. To do problems like this, it's always better to find the components of each vector along X, components of each vector along Y, and then just add them together, okay? So let's do that. I would like to write A in forms of its component using something called a unit vector. It means it's a vector along X or along Y with a magnitude of 1. And we usually show them with I, and we usually show the Y with J. So A would be component X, I, component Y, J. This is how we're going to write it. All we have to do is now find the magnitude. So for A, the magnitude is 5 newtons. Magnitude 5 newtons. The angle or the direction is 105 with positive x-axis. Okay. So let's quick cheat here a little bit. Let's check back this one. Fx is f cosine that angle. The angle was with positive x-axis, with x-axis, positive x-axis. So fx is f cosine theta. So f, which is 5 newtons, cosine, which is 105, I. Ay was f sine that angle. Again, 5 newtons, sine 105, J. Okay, that's my vector A. If I write B also the same way, B is pointing straight up. So the component I of it is 0. The component J of it is 2.2. Okay. Another way of looking at it, the angle that it's making with x-axis is 90 degrees. So if we want to go with our equation, it would be 2.12 cosine 90 I plus 2.12 sine 90 J. This is 0. This will be 1. So you get the same answer. So whether just looking at it or using the angle, we'll get the same result. Vector C, it is pointing only on x towards x-axis. So the x would be 2.12 newtons I plus 0 J. Okay. Once I have the vectors written this way, all I have to do is add all the i's together. So add all these three here, which I've already done the math for you guys. 83.83. Don't forget the I. And add all the j's here, which is going to be 695. We usually like to call this R, stands for resultant vector. So now what I have is a vector that the I component is 0.83 and the J component is 6. Should be much larger, but okay. It wants the magnitude of the resultant. To find the magnitude, I have to use Pythagorean theorem. This is the magnitude. These are the components. Component I, component J. The way to do that is the magnitude R is just going to be a square root of a squared of those two, 695. And this will give you 699 newtons as the magnitude R. So I guess if we want to answer that question, most nearly, okay, it's going to be option A. Okay, questions? All right, so let's do another one. Similar, I'll do it a little bit quicker. This one was a little bit slower, needed more explanation. So we'll do one that uses a slope triangle. This case, remember, slope triangle, component X is A over C, component Y is B over C. Three forces act as shown below. The magnitude of the resultant of the three forces. Same thing. Resultant of three forces is most nearly which one? Okay. We have three forces. Let's call this one 1, so we can kind of keep track of. 2, let's call this one 2. Let's call this one 3. I'm going to do the same thing. Okay. Now I think the problem is starting because there's a delay. Okay. All right, we'll see if the delay starts. We will switch to okay, I'm trying to get this back. Okay. If it doesn't work, that's all right. I have another way of doing this. Okay. Yes, let's just do, that doesn't work. Let's go back to traditional way of whiteboard writing. we're doing this one. Okay. Okay, so the way I named them, I named this one 1. The difference is my handwriting is now going to be terrible, so I'm using a pen pad, which is not as convenient as an iPad. So, all right. So I'm going to do the same thing here. Let's write vector 1. I don't know if that's a proper way of writing a vector, but anyways, you get the idea. Is going to be the magnitude, 260, something over something. So I'm looking at x component, or rather minus x component. The way to do it, so it's going to be 12, 5. So I think this is going to be 13. So 12, 5, 13. So that 13 always goes on the bottom. It's just a matter of, is it the x or is it the y? When you're looking for x component, always take the side that is parallel to that axis. So for x, I take 5. And this is going to be minus I, because it's pointing towards minus x. Okay. For the j component, it's going to be 260 and move my camera here. 260, 13 goes down all the time. This time that I'm looking for y-axis, and this is plus y-axis, we'll take the one that is parallel to y. So we'll take 12 over 13, and this is going to be j. So that's my vector 1. 2 is easy. It's pointing straight down. So the I component is going to be 0, 0i, plus 50, which is pointing to negative j. Vector 3, the magnitude is 300. So it's 300 something over something. 3, 4, this one would be 5. So 5 goes down all the time. I'm looking for x component, so I'll take the one that is parallel to x. 4 over 5 is pointing to positive x, so I'm going to put I. The y component is going to be 300, something over something. 5 always goes down, and the one which is parallel to y-axis is 3. It is pointing up, which is plus, so I'm going to just put j next to it. Okay. If you do the math, again, all of these you need to add together, which will be 370 I. If you add all the j's together, it is going to be 140 j. This will be my resultant vector. Same as before, to find a magnitude is asking for magnitude. To find a magnitude, all I have to do is find square root of sum of the square root of those two, 370 plus 140, which will give you 396 newtons. Okay, let's see the choices. Right there. Okay. Questions? All right. Let's look at some other problems that deal with free body diagram. A heavy roller is held in equilibrium on a frictionless plane AB by force F as shown, which diagram correctly shows a vector polygon. Let me do something here. Let's have this here to just quickly go over free body diagram. Okay. A heavy roller is held in equilibrium frictionless plane AB by the force F as shown, which diagram correctly shows a vector polygon of the force acting on the roller. So what we are dealing here is something called a free body diagram. or FBD. So this is a diagram that shows that rigid body or particle or truss or frame or machine or whatever we're dealing with, it will show all the forces acting on that body. And it has 3 steps. And if you follow these 3 steps, you can draw a free body diagram of anything without any problem. Step 1 comes from the free. So step 1 is to isolate your, whatever it is, isolate the body. Could be a rigid body, could be a particle, doesn't matter. That means remove all supports, constraints, all of that. Remove everything. Okay? Step 1. Step 2 is add active forces. These are the forces that are trying to mess up the equilibrium, trying to mess up the equilibrium. Yeah, I don't know why it does that lines. Equilibrium. In other words, forces that are trying to move it, you know, move the object, move the body, move the particle. Step 3 is to add reactive forces. Those are the forces that are trying to stop the active forces, trying to maintain the equilibrium, trying to maintain the equilibrium. Okay? In this, step 3 is when you deal with a lot of supports and all of that. And I have a rule for supports. So I ask all my students to draw a little quick table. Okay? Whatever support you have here, put it here, put an X, put an Y, put a moment. And then ask this question: does the support, does it move in this direction? Does your support move in X direction? It's either yes or no. Does it move in Y? It's either yes or no. Can it rotate? It's either yes or no. And wherever you see a no, that's where you are supposed to put a force or a moment in that direction. Okay, so this is to figure out this reactive forces. So let's look back at the problem that we have and try to draw the free body diagram for it. It's this one. A heavy roller is held in equilibrium. So we want to draw free body diagram of that roller. Step 1 is isolate, meaning just the roller itself. Step 2 is active forces. Okay, I see one active force. It's a heavy roller, so that tells me that this roller should have a weight pointing down. Reactive forces, the forces that are trying to maintain the equilibrium. There are 2 forces here that are maintaining the equilibrium. One of them is force F. The problem is tell us that, hey, it's held by force F. But also this, don't forget the surface. So force F is applied. And there's a contact here, which we usually call it a smooth contact or a smooth surface. Creates a normal force. Perpendicular to the surface. So this will have a normal force perpendicular to the surface applied to the roller. So these are the 3 forces acting on it. W is the active force, F and N are reactive forces. Okay, this is kind of similar to one of these options, but not exactly, because the problem is asking us diagram, which diagram shows correctly a vector polygon. So the way it works is just you gotta move the vectors around a little bit without messing their direction or their magnitude. F, W, And if I put N right here, that will totally makes a polygon as the problem is asking. So which one do you think is the polygon that we're looking for? Anybody? Okay, let's see. C, yes. So option C. So my scale is a little bit off here, but this is basically F, this is the normal force, and this is the W. I think they draw W. Well, maybe it says because it says heavy, but that will give you the free body diagram of this roller. Okay. All right. Let's look at another one, free body diagram, and which has a support on it. Okay. A rod is shown in the figure below. If the weight of the rod is neglected, which of the following is a correct free body diagram? All right. Before looking in the figure, getting confused, let's just do the 3 steps of the process. Step 1 is isolate. We want to draw the free body diagram of the rod, so let's just draw the rod. Step 1 done. Active forces, the forces that are trying to mess up the equilibrium. I see a 2F, and I see another F going this way. Okay, which already that eliminates this one. So we know option B is not. But the other ones, we still don't know. They're all very similar. We have two surfaces here. It's a pin. This one, again, is a smooth surface. So let's make that table really quick here. Pin. And let's call that smooth surface, let's call that B. Easier. X, Y, M. The question is, does it move? So let's look at the pin. The pin is if you hold your pen in your hand with 2 fingers like this. So your pen can easily rotate around your finger or where you're pinning your pen, but it cannot go up or down if you're holding your hand steady. So this pin, if I have X and if I have Y, does it move in X? Nope, it does not. Does it move in Y direction? Nope, it does not. Can it rotate around the pin? So now the question is, does it rotate or not? The question should be asked only looking at the pin. Only looking at the pin. Doesn't matter if it's stuck at point B, or doesn't matter if it's even welded to the ground. The question is, does the pin let this rod move? Yes. You know, the pin in itself, it lets move. So it's a yes. The only forces you need to put is the one that show up as a no. So all I have to do is put a force in X or Y direction. Let's call it PX for pin and PY. Direction doesn't matter because it's an unknown. I don't know it, so you can put it any direction you want. So that should not matter. Point B. Does it move in Y direction? It can go up probably, I don't know, but it certainly cannot go down. So I'm going to put a no. Can it move in X direction? Again, I'm only looking at this surface. Only. If this rod was on the surface, yes, it would probably freely go X and Y. Yes. Can this move, rotate around point B? Again, if I only look at point B, yes, it can move. So the only thing that I need to consider is a no. So this will give me BY, something like that. All right, let's now look back at options. Option A, absolutely not, because this force is wrong and it's missing another force there. So option A is also rejected. Option C, let me check. This checks out. I told you the direction doesn't matter. 2F and F checks, and this checks too. Option C is okay so far, but let's check option D. This checks out, okay, but this is wrong. So the only option, correct option here would be, what happened? Keep. Would be option C for this problem. Questions? Pointer. Okay, questions about this one? We'll see why it doesn't work. Okay, so let's look at another one. Let me see if my pen is working now. Oh, yes, it's working. All right, a cylinder weighing this much rests between two frictionless walls as shown in the figure below. The wall reaction N at point A is most nearly. Okay. Step 1 is to draw my free body diagram. Point A and B, both of them are smooth surfaces. So, and we talked about it. I have no idea what draws a line through it. It will generate a normal force perpendicular to the surface. Okay. Or you can make that table, see if it moves in X and Y, and just put the forces. But I'm going to do it a little bit quicker here. Step 1, isolate. Step 2, active forces, which is the weight of it, which is 120 newtons. Step 3 is 2 forces perpendicular to the surface. Whoa. Oops. Normal force, which we can call it NA, and another normal force at B. Sorry, my pen is acting weird. Okay. So yeah, ignore this part of it. All right. NA, it is 3, 4. This one is perpendicular to that, so it's going to be 3, 4. It's going to get switched. All right. The way to do it, which one we are looking at? Wall reaction at point A. So we are looking at NA. So with one equation, I can figure that out. Summation of all forces in y direction is going to be 0. Anything that points up, I'm going to put plus next to it. The first one I have is NA. What is the vertical component of NA? 5 goes down here, I told you, all the time. Should I use 4 or should I use 3? I'm looking for vertical component of NA. Anybody? 4 or 3? 4. So, because I'm looking for y component, I go with the one that is parallel to y. Remember? NA, it's pointing up, so that's going to be plus. Then I have a minus 120 newtons equals 0. All right, good. I just have one unknown, one variable. If you do the math, NA will be turn out to be 150 newtons. Okay, let's see. Option C, 150 newtons. Questions about free body diagram? I have one more free body diagram problem that has distributed load on it. We're doing really good on time. Okay. So kind of same thing, free body diagram, but it has requires free body diagram, but it has a distributed load. Beam AB has a distributed load as shown and supports at A and B. Okay. If the weight of the beam is negligible, the force RB is most nearly how much? Okay. The first thing we got to do is get rid of that distributed load. Okay. So the way we do that, let me get rid of this whole thing. So I have a blank sheet here for you. Okay. The way to do that is you're going to see two forms of distributed load. One is known as rectangular. Okay. They're not going to give you an equation or a parallel or a polynomial type of load. They're going to give you a, let's call this W. And let's call this length L. Okay, just for sake of theory. They're either going to give you this, or they're going to give you a triangle kind of load that starts at 0, but it ends with W. Okay. Again, same thing. L. Let's call it W2, L2. So the way to do it, you have to find two things. First is intensity of the load, or just the magnitude. We know it as magnitude, which that one is area under loading. In other words, just area of the rectangle. Okay, this length is W. So the intensity of load is just going to be W multiplied by L. The other thing that you got to find is location of the force, which is going to be centroid of area under load, which in this case, it's a rectangle. So the location of it, centroid, we usually show it with X bar. It's just going to be L over 2. These are the two things that you have to figure out. For the second one, same thing. The intensity, let's call this F2, of the load is going to be area of triangle, which is half of the base multiplied by side. So half of L2 W2. The location of it, X bar of it, is going to be centroid of a triangle. Centroid of a triangle is located 1/3 to the base, or 2/3 to the other side. So it really matters which way you're measuring. Okay, so let's measure from this point. Let's measure from A. X bar from A is going to be 2/3 of L2. Or X bar from B is going to be 1/3 of L2. So these are the two that you need to know. Sometimes they give you a combination. They might give you something like this. See, it's a triangle sitting on top of a rectangle. Sometimes they might give you a rectangle and then it goes to a triangle, something like this. Okay, so anyway, you should be able to always break it down into a rectangle, a triangle, or a combination of those two. So let's look back here. I have to find location, and intensity of this force. The intensity area under curve, which is going to be 1/2 of 3 meters, 8 kilonewtons per meters and meters, 24, 12. Okay, 12 kilonewtons. The intensity or location of it, let's find location from A, is going to be something about here. So this is going to have 1 meters. This is going to have 2 meters. So it's going to be 3 plus 2/3 of 3 meters, it's going to be 5 meters from A. Again, depends on where you want to measure it. So now I have something like this. So now let's get rid of the distributed load. I have RA, I have RB, I have a force of 12 kilonewton located at the distance 5 on this side, 1 on this side. All right. Now I can go back and read the problem, see what it was asking. It is asking us to find force RB. Okay. So you have 3 equations in general solving problems. You have summation of forces in direction x equals 0, summation of forces in y equals 0, or summation of moments about a point. Any point you can take is going to be 0. So if you want to find RB, which one of these equations will you use? You need only one equation and you are able to find RB. Which one would you use? You can unmute your microphone and just speak if you want.
Summation of moments.
Okay, about which point would you take it?
About point A.
Okay, exactly. Summation of moments about point A. The reason is we say this RA is going through point A. If a force is going through a point, you don't need to worry about the moment because it's not creating a moment about a point, about that point. Summation of moment about point A, I'm going to add another sign convention here. Anything that rotates this way, I'm going to put positive next to it. All right. Summation of moment about A, RA goes through point A, so it's 0. There's no moment. Next one is 12. Okay, moment is, remember, is force multiplied by distance. This distance is perpendicular distance between point, that point, whatever point you are looking for, and line of action of that force. Not just that force, but the line of action of that force. 12 kilonewtons, perpendicular distance between point A and line of action of 12, which is 5 meters. Okay, keep moving. The next force I see is RB. The perpendicular distance between that point, point A, and RB, which is 6 meters. I don't see anything else, 0. Okay, one last thing I gotta do is check the signs. 12. So the way I tell my students to check the sign is hold up your pen and pin it at that point that you are seeing. So I'm gonna hold up my pen, pin it at point A, and then push down as if I'm pushing down with that 12 kilonewton, pushing down. And then kind of track which way your pen is rotating. So if you push down, pin at point A, push down at point 12, it's trying to rotate the beam this way or clockwise. And then I go back and check with my sign. I said anything that goes counterclockwise, I'm going to put plus. So I have to put a negative right there. All right, point B. Pin at point A, push up as if you're pushing with RB. It starts to rotate this way. I have to check with my sign. Yep, those two match. So it's going to be plus. There you go. That's how you can figure out the signs. Simple equation. If you do it, you will get B of 10 kilonewton, RB of 10. If the problem was asking find both of them or find RA, all you have to do is next use summation of forces in y equals 0. So 10, 12, so that means this one is 2 kilonewton, which makes sense because look, majority of the load is on the other side of the beam, right? So it's still pushing a little bit on the other side more. So therefore that one is taking a lot more loads. Okay, questions? It seems, feels like a lot of answers were C for some reason. I don't know. It might just be these set of examples that we have. Questions? Okay. You can ask questions anytime later too. We can go back to these problems. Okay. All right. The moment of force F, Newton meters, shown below with respect to point P is most nearly. We in statics usually, instead of with respect to, we say about point P instead of with respect to. So that's the same thing. Find the moment of that force about point P. So for problems like this, I always tell my students to break it down. Okay, moment is, break down the force. I mean, moment is force multiplied by distance. This distance, I just told you, it's perpendicular distance between P and line of action of F. Line of action of F is right here. Okay, so if you can find this perpendicular distance, which doesn't look much very perpendicular, if you can find this D, then all you have to do is do 500 multiplied by that distance D. But I'm thinking it would be difficult to find that distance D, a lot of trick. Okay, so easier way is to find, instead of doing this, find the component of that F in X and Y. Okay, I'm gonna have Fx, which we talked about it. That was the first example we did. What is the component Fx here? We have the angle, we have the magnitude. What is Fx? Remember, similar to the example that we have, 500 angle theta. This Fx was what? 500 cosine 30. Yes, someone said it. Sorry, I didn't see that. 500 cosine 30. Once you know that, the other one is easy. 500 sine 30. Okay, now this is much, much manageable and better. So the moment now about point P is going to be summation of two forces, two moments. The first one, which is going to be 500 cosine 30. Cosine 30, which is going to be 433. At a distance. The distance is perpendicular distance between point P and line of action of F. Perpendicular distance. This is line of action of that force. Perpendicular distance between that point and line of action is right there. It's given 100 mm. Okay. The next one I have is 500 sine 30, which is going to be 250, at a distance. Again, perpendicular distance between that point and line of action of that force. Line of action is right here. Perpendicular distance is 300 mm. Okay, one last thing I got to do is the sign. I use the pinning method. So P, pin at point P, push up with 500 sine 30. It is starting to rotate this way. Pin at point P, push the other way. It is starting to rotate the opposite way. So one of them is going to be negative. I forgot to put this here. Anything that goes counterclockwise, we usually put plus. This is a very acceptable convention, sign convention. And this one is going to be plus. Here, it will give you 31.7 Newton meters. Okay. 31.7. 31.7. Oh, we have two of them. So that sign is going to be important. So it turned out to be plus. Okay. Plus means it should agree with my sign. My sign is counterclockwise. So this guy here is also this way or counterclockwise. So good thing we kept track of signs. So it's going to be this one. The streak is broken. It's not C anymore. It is A, counterclockwise. Questions? By the way, if you didn't notice, because the problem was asking for Newton meters, I just did a unit conversion, which is basically just putting a dot right here. If you put a dot there, it turns it into meters. Okay? Questions? Okay. Let's do, yeah, we're doing good on time. All right, let's do one. In the figure below, the coefficient of static friction between, okay, now we're dealing with friction, between the block and the inclined plane is 0.25. The block is in equilibrium. As the inclined plane is raised, the block will begin to slide when, okay, so it's resting on that surface, we start raising it, right? Obviously, we can't go forever. At some point, that block is to start to slide down. So before I solve this for you, I mean, you got to draw a free body diagram and use the two equations that we have, or three. Before doing that, can you just look and guess which answer is going to be? Because sometimes in these problems, you don't have to solve it. All you have to do is just get rid of the bad answers or know which one you're looking for. So someone is saying C. What else? So before solving this, let me give you a theory. When it comes to friction, a box sitting on a surface, there will be a friction force. I have no idea why this does weird stuff today. There's a friction force. There's a normal force. At the onset of moving, okay, or we call it pending motion. This F is going to be coefficient of friction multiplied by normal force. In other words, it's going to be mu n. Okay, two forces, I can find the resultant force of these two, and it's going to be resultant force R. This is N, that is F. So if I want to take this angle here, let's call it angle phi, because it's usually referred to as phi. If I want to write tangent of phi, based on this triangle that I'm looking at, is going to be mu n over n. So tangent of phi is going to be mu. This is just a general theory about friction. Okay, this is the first thing I teach in lectures in friction. So this box has a weight of like W. I mean, this is not a free body diagram in any form. And you're trying to move it with force P. That's the friction forces that are created. So based on that, if you look at the answers one more time, can you tell me which one is going to be the answer now that you know this? D. Now I see some people are saying D. So if you know this theory and if you're just learning, this is just a general friction. If you put any box with any weight on a surface with a friction coefficient of 0.2 or friction coefficient of mu, the angle that this box starts to slide down is going to be tangent of that. But let's say you didn't know that. You know, how are you supposed to remember that? So let's just draw the free body diagram here quick. Free body diagram, 3 steps. Isolate means remove everything from it, just the box. it has a weight W coming down. That's the only thing. The only other forces applying is it at the friction. So if we increase the angle, the box eventually will starts moving down. So that means the friction is going to be opposite of that movement, okay? And it always has a normal force perpendicular to surface. This is it, okay? So we got to solve for friction force, okay? The way I like to do it is I am going to turn my axis a little bit. I'm going to call this one X, call this one Y. Because in that case, then I only have to deal with one of the forces. Need to find the components of that force, okay? Let me write summation of forces in X direction equals 0 for equilibrium. Anything that is pointing with that angle in that X is going to be 0. I'm rotating my axis, okay? All I have is a W sine theta or sine phi. Let me quickly draw it for you. It's going to be a W sine phi, and it's going to be a W cosine phi. It is pointing against my sign, so I'm going to put a negative next to it. The other one is plus F, which is going to be mu n also, equals 0. The next thing I'm going to write is summation of forces in Y equals 0. Anything that is pointing this way is going to be plus. I have a W cosine phi now, and I have a normal force that is pointing up. All right. So from the equation below, I can figure out that N equals W cosine phi. So let's put it back up there. Minus W sine phi plus mu W cosine phi equals 0. Okay, kind of running out of space here. I'm going to write it a little bit smaller here, but let me change my pen color so it's easier to keep track of. So therefore, W sine theta or phi or theta, I don't know, it's phi. Phi equals mu W cosine phi. So mu is going to be tangent of phi. We have 0.25. People already said that long time ago. It is option D. But again, as a general rule, remember that relation between tangent phi and mu. So if you see a problem like this, boom, you don't even need to do it. You can pick it and move on to the next one. Okay. Any other questions? Or I should say any questions. Okay. So let me skip this one. Okay. This is a long problem. I want to get to trusses and stuff. If you get time, we'll definitely get back to this one. This is a friction problem, but I'll give you the answer if you want to. Okay. Mark all of the 0 first members of the simple truss below. Okay. 0 first members. 0 force members are the one that are not carrying any load. Or if you write an equation for them, draw a free body diagram of a joint, the forces that you're going to find in them is going to be 0. So someone might ask, what are the reasons we include them in a truss? There are 2 reasons. One is sometimes for construction it's needed. Second is if anything on the truss loading changes, those members that are not currently carrying load might come in and help and carry some load. So that's for change of load and also construction. But anyway, the way to figure them out, you have to draw a free body diagram of a joint. And I'll pick a joint here. I'm going to draw a free body diagram of FBD of B for you guys. Okay, and I'll explain why I'm picking that. Free body diagram, I told you it's the same thing. Isolate. There you go. Remove everything. Put active forces, reactive forces. In the case of trusses, they're kind of mixed together. So I have a force going BC this way. I have a force going this way, BA. You can put them in compression or tension, meaning going away or coming in. Doesn't matter because I don't know it. I'm just always used to drawing in tension. And BG. Okay. I'm going to turn my axis again, X and Y, and write summation of forces in Y direction being 0. Anything that points up is going to be 0. And I need to go back and look at joint B. The only force I see is BG. There's nothing else. So therefore, BG must be 0. So that is my first 0 force member. But now I tell you why I picked point B. So when you're doing trusses, look for members that are like this. I'll call this A, call this B, call this C, call that D. Look for 2 members that are in same direction and a third member with any angle, doesn't matter. Here it's 90, but it could be any angle. That member that is branching out from the other 2 members is always a 0 force member. Okay, so that's why I picked point B. Do you see any other members that you can pick that has the same characteristics here? 2 members in one direction and the third one kind of branching out? Look here.
Would point E?
Point E, exactly. It's the same case. You can draw the free body diagram same way. EC is going to be 0 force member. Okay, BG, if they're not carrying any load, you can remove them from the truss. Okay, if I remove member BG, if I remove it, what happens to GC? Isn't that the same thing here? See that? Because BG is 0, as if it doesn't even exist. So therefore, this is another 0 force member. Now look, CG and CE, I have removed them because they're a 0 force member. So now let's see what happens to point C. This one is removed. There's nothing in CG, and there is one going this way. Do you kind of see the same trend? 2 members in one line, the third one. So this is also a 0 force member. I know it doesn't make sense because how can we remove all of that when we still have a truss? You're absolutely right. But with this arrangement, none of those members are carrying a load. Therefore, they're all 0 force members. Okay. So when you get a question of 0 force members, always remember this rule. If there are 2 in one line, the third one branching out, that's your 0 force member, and you can work your way on that one. Okay. Questions? I have two more problems, so we're doing good on time. All right, so let's look at a scary problem. Okay. The first when I saw this, I was like, whoa, this is too much work. But usually problems that look as scariest, they're the easiest to solve. All right, so we're gonna get to this. So let me give you a little bit of theory here that you're gonna need it. Yes, let's clean this up. So when it comes to trusses, you have 2 options. I kind of like the color blue honestly better. So let's go with that. Okay, when it comes to trusses, there are two ways to analyze them. One, we call it the method of joints. The second one is called the method of sections. Okay, the difference is in method of joints, you draw free body diagram of each joint. In method of sections, you draw free body diagram of a section. Or I shouldn't say section, I should say a half of a truss. What do I mean by that is you have a truss, okay? Something like this, could be any shape or any form. Trusses are usually pinned on one side, usually on a roller on the other side, to allow for expansion, deformation, all of that. If the problem is asking usually one or two of the members that are kind of in the middle, if it says find the forces in BC or BD here, that's when you got to use method of section. The way it works is you make a cut. You cut your truss in half. And I use this example in my classes. I say, you know what? So students have class with me, they know. It's an arm, hand. Sorry, it's a little bit graphic. When you make a cut, that's when you will show the internal forces or blood or whatever that can come out of it. It's the same thing with truss. When you make a cut, I'm going to just draw that half that I'm making a cut. It will show the forces that are in that member, and they're going to expose themselves. Okay, so now let's go back to our problem and just try to make a cut here. The problem is asking member BC, which is, let's find it, BC. So I have to make a cut that goes through that member and cut my truss in half. Okay, that's the cut I'm going to make. Then you have to draw a free body diagram of that half of truss. Step one, outline, isolate. That's good enough. Step two, active forces. 3, 3, 3, 3. All of them are KIP. Step 3 is reactive forces. I told you, when you make a cut, the forces are going to show themselves. I made a cut, so it's going to be BC going this way. Another one, I'm going to make a BI going this way. And another one, IJ going this way. Okay? And if you are smart about it, usually with one equation, you can do everything. I'm going to pick point I here, and I'm going to write moment about point I being 0. Okay? You have three equations that you can use. Summation of forces in X, summation of forces in Y, summation of moments about any point you want to pick. I picked point I because 3 of the forces are going through it. I don't even have to worry about it. And the actual force that I'm caring about will stay out of it, so I can do it. So one moment, I'm going to go quicker here. Every force, you have to draw a moment about it. BC, perpendicular distance between point I and line of action of BC, it's right here, 5 feet. 3 IJBI, they all go through point I. I don't have to worry about it. Now I'm going to write this 3. The distance between point I and that 3 is right here, which is how much? 5. They're all 5. The next 3 is right there. Perpendicular distance between point I and that force is this one, so it's going to be 10. Last one is right here, perpendicular distance. Again, same thing, 15 feet, 3 kip equals 0. BC is trying to rotate this way, so that's with my sign. All of the other ones are trying to rotate against it. So I'm going to put negative. All right? This will give you a BC of 18 kip, which is, kip is 1,000 pounds. So 3 kip is 3,000 pounds, basically. So you see this problem looks scary, but in reality, it was just really easy with, if you make a smart cut and pick a good point to solve it. It shouldn't take more than 30 to 45 seconds if you do it quick. Questions? All right. Let's do fun stuff. Integration. Okay. Consider the following graph. All right. Which of the following expressions gives the distance from the y-axis to the centroid of shaded area? Okay. We're talking about centroid. When it comes to centroid, remember this. The distance from y-axis is x bar. It's it's opposite all the time. Okay. So we're looking for x bar. That's one step. X bar is something called x. We usually call it x or x tilde dA over integral of dA. This is one of the topics and problems that can be intimidating or scary, or you say, well, this takes too much, but usually these problems are really easy. Okay, so let's look at it. This is what we're looking for. So some people might ask, what is that x tilde? X tilde is the distance of the center of an elemental area element. Okay, dA and A. All right. For problems like this, what you got to do is quickly draw a little tiny element of area. Okay. And let's find the width of it and the length of it. So the width of it is what? No, sorry, the length of it. The width of it is going to be dx. So what do you think is the length of it? If you figure that out, a lot of your problems are solved, and you can probably figure it out right there. When you look at this figure, what is the length of this element? Anybody?
Is that just going to be the x minus x squared over 3?
Yes. Yes, exactly. So what is going to be, I'm going to call this y2 graph, which is x. Okay. I'm going to call this one y1, which is what? X2 over 3. So this length here is y2, y sub 2, I mean. This little length here is y1. Okay. So the difference between those two, this length is y2 minus y1, as someone said, is going to be x minus x2 over 3. So if I want to find the area, is going to be just this multiplied by dx. So let's figure out, can we already pick our choice yet or no? This one is okay. This one is okay. This one is okay. Yeah, there's too many of them. So we know for sure this is not going to be the case. I think we got to figure out the top part too. So the top part is going to be, just has an x tilde in it. So I'm going to write down this one. It's going to be x minus x2 over 3 dx. The top part is going to be the same. It just has an x tilde in it. The distance of the center of this element until y-axis, which is going to be here, which is just x. So need to have an x multiple to it. So let's see if we can figure that out. So now it's going to be x2 minus x. So basically is x2 minus x3 over 3. Dx and dx. Okay, let's see, figure out which one. X2 minus x3. This sounds okay, but let's just check the ones quick. Nope. Nope. So it's going to be option B as my answer. Again, the key to this problem was just drawing that little element and figuring out that if that was the case. Okay, questions? Any questions about any of the stuff that we covered? I think the time is up. But if there's any questions, I'd be happy to answer the questions. My email is up there on all the slides. But here is also my email. If you guys have questions or anything, I'd be happy to answer if you reach out to me by email. Usually these days I work from my home office, so I'm not in my office. Otherwise, my office door is usually open to whoever wants to stop by and ask questions. But I'd be happy to answer any questions if you have now or later through the email about any of the stuff that we covered.